Negative 21
Okay,
minus
so this is
11.
your original slope.
Negative 32 F, which is negative
So
16.
second one, with the parallel line, you know the slope of it. If it's parallel, the slope has to be the same.
All right, guys. It's always interesting the way to choose to approach this subject. There's a lot of different ways I could choose to kind of broach the subject, but let me try this. Why not?
Is that a straight line?
Yeah, it's supposed to be. Just pretend like it is. Here's f of x. Let me ask you one quick little review question. What is f of 2? 3. Now, here's the trick with this section. In this case, can you tell me, can you answer this question here? What does x have to be to make the output negative 1?
Negative 1.
Yeah, what x value has an output of negative 1?
That is negative 2.
Negative 3, right? You with me? Are you guys with me? Okay. So this would be x equals negative 3. Now, you could answer that question, which means something interesting about this function is going on compared to this function here. Start him off right here. Say it's like this. Now, what difficulty do you have? Speaking like me, but what difficulty do you have when I ask you what x value gives you an output of negative 1? There's two answers. You can't answer that really. The way I've worded it, it's like I can't answer that question, dude. There's more than one thing that gives me an output of negative 1. All right, how are we doing so far? Okay, so there's some kind of problem here. Not really a problem in general, but it's hard to go backwards. It's hard to see what caused an output of this to happen. Here I could tell you, in fact, anywhere along here, if I was a lot more precise in the way that I drew this, if I ask you what input gives you 3/2, you can tell me it looks to be 1. There's no question about it. There's no ambiguity. It is 1 causes that to happen. So what is it fundamentally about the difference between these two graphs that actually identifies why I'm able to do that here, but I'm not able to do that everywhere here? What has to happen in order to go backwards, to have a y value given to me, and I can find the x value that caused it to happen? That's right. What's the thing that this guy did that this guy did not do? Came back on itself like that, right? You with me? Now, so this kind of thing here is really bad because it's not even a function. So now, this is kind of the same idea just turned on its head. These are both functions. It's just that this function I can't work backwards as easily as I can with that function. Because I don't know which one. You see, okay, we're in a situation where it's 1 foot below sea level. What does that mean? I don't know. It could mean 2 things. Oh, shit. You know, I have this weird horror movie in mind about that's important somehow. But so what's really going on here is, let me see if this makes sense. To be a function for every x, there must be only, it can be only 1 y, right? Mathematical equivalent of Highlander. For this kind of thing, this is what's called a 1-to-1 function. Or like that. 1-to-1 function. For this to be true, not only does it have to be a function, but it also has to work the other way around. For every y, there's only 1 x. Now, if you think about it, that just makes freaking sense. That's the only way I can always tell you exactly where a value came from. For an output of this, where did it come from? Well, that means every y must have only 1 x that leads to it. or else I can't really answer that question, right? All right, maybe so. Okay, so these one-to-one functions are interesting because there should be somehow more I can do with them. And the funky thing is, since it just really turns x and y on its head, let me do this. So we got the idea of it, we got the definition of it. Let me give you another visual here. So if I have a function that is one-to-one, that must mean there's a way to turn the function around. If every y has only one x, I should be able to turn the function around. I should be able to solve for the other variable easily. How are we doing so far? So, for example, this is a function. Can I solve for x? Truthfully, can I? Not really. Because what happens when I try to solve for x? I get two functions. I can't solve directly for x. I get two options. So is this a one-to-one function? Because there is, for every y, is there only one x? No. Kind of with me?
There's a plus and a minus.
Yeah, there's two x's for every y. So it's no good. Yeah.
That first function was not one-to-one because I had a set. So it was one, right?
So I had this function was fine, the one that went like that.
Yeah, but then the one
This
below,
one was no good, whatever it did, like that.
yeah, that's not one.
Yeah, exactly. So I'm trying to get you the visual of what this really means. This looks like this. Therefore, it kind of leads to a nifty test. Just like the vertical line test, I can't have it come back on itself in this direction either. So to be a function, it can't come back on itself like this. With me? It can't do this to be a function. Now, to be a one-to-one function, it can't do that idea in the other direction either. So not only does it have to pass a vertical line test, it has to pass a horizontal line test. Cool. If it passes both, not only is it a function, it is a freaking one-to-one function. And if I know it's a one-to-one function, I know the opposite function exists. I know I can solve for a real function that gives me the opposite. It does the opposite of what the original one did. Maybe. Okay. Y'all just generally look uncomfortable. So let me give you another, maybe a bigger graph here. You can see a little better. Okay. Stay with me. Here we go. So let's just make it straight line. Okay. Now, this is very just conceptual here. But this function goes through the points. Somebody help me out. This is the point -2, -3. This is -1, 1. This is 1, 2. And this is 3, 3. Cool. So my funky scale makes that a straight line. It really shouldn't be, but oh well. Now, if I want to visually get the opposite function, and think about what the opposite function would do. So whatever, if a function in this case, what can I write about this function here? What is f of -2? -3, right? Because it goes to the point -2, -3. So my opposite function, which I'll call O for right now, why not? What should it do to -3 then? It takes it back to -2. The opposite function should undo whatever the hell the original function did. You with me? So if my function was x plus 5, the opposite would be x minus 5. Very simple example. Somehow it involves opposite operations. How are we doing so far? We decent? Yes, ma'am. I'm getting there, exactly. Yeah. I don't know why I don't want to say that word, but yes, it's the inverse function. Cool. So I can draw the inverse function before I even know what the hell, I don't even know what the hell f is. But I could draw the inverse function up here. This goes to the point -2, -3. So my inverse function has this symbol. What point does it go through? Yeah, -3, -2. It also goes through the point 1, -1, 2, 1, and 3, 3. Is that cool? It's that simple. That's awesome. And some problems will be asking you to do exactly that. And that kicks ass. You just turn them around. Don't change the sign. This is all it does, is it undoes what the other function did. So it's going to go through, let's see, where am I at? -3, -2, 1, -1, 2, 1, and 3, 3. It's going to look like this. You guys see anything interesting about that besides my scale sucks, but do you guys see what's trying to happen there? Reflection around where? Where's the mirror?
Average.
I know what you mean, sort of, maybe. It's around the y equals x line. The mirror is right on the y equals x line. And why does that make sense? What does this thing do? Doesn't it reverse the y and the x? So shouldn't it flip over the y equals x line? Because that's exactly what each point does. It's exactly equidistant there, supposed to be. They're supposed to be crossing each other, but my scale was better, to be honest. You guys semi with me so far? Still? Good. So in order for an inverse function to exist, I have to pass the horizontal line test, and that's why I drew this the way I did. Right, it's easier for if I just start low and go high. That keeps me straight. It just can't come back on itself. Okay, so let's get a little more technical. So graphically, this procedure is very simple. Just take every point you see, flip it, and then regraph it. And then you've got the inverse. Right? No big deal. Yeah? That's where I'm going next. So visually, it's easy. Now, what do I do if I'm given just an equation? I don't want you to have to graph every single one of those and do it that way. There's got to be a quicker way, an algebraic way. Maybe something relating to the idea that what it fundamentally does is it changes the x and the y. And we saw that in the points. So here's an example. Given this,
So then why?
how do I find f inverse?
So replace f of x with y and solve for x.
Yeah, so I'm going to bring back in what is f of x, also known as back in time y. Yeah, let's bring that back in. I love it. So now I do exactly what we did on the points. I switch the x and the y. And the beauty of this is it just makes so much damn sense. It's not even funny. The minute I do that, I'm going to solve for y again. So if I switch those, I want my inverse function to be the function that does all the opposite stuff. That only makes sense, right? If I want an inverse function, an opposite function, it's got to do all the opposite operations. Well, switching the x and y, I'm hoping you guys have bought into that now that we've done it a couple different ways. If I resolve for y, what do I end up doing? What's the first thing? Solve for y. What do I do? Please don't say cube. It'll make me cry. Subtract 5. Get the 5 out of the way. And now you.
Cube.
Cube both sides.
Make the teacher cry.
That was not meant to be some kind of a challenge to make you cry, by the way. That might make you cry, but so would this. No, just keep that out of here. Yeah. No, that's fine. Don't freak out. So I want to point this out. Some of you guys might realize this is a shortcut, but it will lead you wrong sometimes. And plus, I need to see the work anyway. But from the very beginning, I knew my inverse should be subtracting, and I knew that it should be cubing, because I can currently see addition and cube rooting. This process just puts them all in the right place, for one thing. But realize, what's the last thing I do here? And what's the first thing I do here? So it just reverses the order and reverses the operations. You with me? Sort of. You have to know all that crap? No, you just do this. You don't have to guess ahead of time. You just do it, and there it is. All right. Now, how do I verify that these are inverses? You could graph them.
You input it in the inverse into the function.
I like it. I like it. Exactly. You could graph them, but then you couldn't really tell, is it exactly y equals x where the mirror is, or maybe you're off by, like, maybe it's y equals 0.9999 in x.
Put a few points.
You can't tell from a graph, especially your freaky window that squishes everything on that way too expensive calculator. Give me a freaking real window that doesn't squish everything. But the way to do it is just to plug one into the other one. This is officially now what we consider to be f inverse. That's the inverse function of f. So, really, in symbols, what am I doing here? If I plug f inverse into f, what should those do?
Cancel each other.
That's what we keep saying, right? That does the opposite of what that does. So whatever one does, the other one's going to undo it. You should end up with just x. So if I do that, just plug that function in. So I'm going to put it right there, right? Plug the inverse function into f. I'm going to get the cube root of this. Of course, here the cube root and the cube cancel. And the 5 and the 5 cancel. So there you go. I just verified that it is the inverse. If it works one way, it has to work the other way. It's kind of nice.
So here that says y equals x, right?
Yeah, it says inverse equals.
Or the f?
It says that these two cancel each other. Yeah, I like it. So one of my favorite problems to give.
Oh boy.
Another way to say that same thing is, this will be on the test. So that's kind of a hint. Is this kind of problem. There you go, Jeff. Now you're thinking. This always freaks people out, and this is where people suddenly revert back to bad habits like dividing by f somewhere. Like, I got to get x by itself. Let me divide the f out of there. No, I can't. Can't get the f out of there like that. It's a weird day for things happening outside. If it was this, what would you do first? Subtract 5, and then what would you do? Square, because that's sort of the opposite. It has problems there, but that's the idea, right? So we do the same thing here. My x is there. I get this thing by itself first. Subtract the 5. Now here's where some of you guys are going to balk a little bit. What do I do to both sides to free this up? This is stuck inside whatever this function. I don't even know what the hell this function is. Because it's some funky ass function. I don't even know what it is. But I know how to kill it.
Divide it?
Can't divide it. This is not me f times this.
Oh, find the function.
I take the what of both sides? The f inverse of both sides. It's just like squaring both sides. Because what does it mean when I square both sides? I'm applying the square function. What does it mean when I cube root both sides? I'm applying the cube root function. So what am I doing here? I'm applying the, I'm not really sure, it's just the opposite function. That's all I know. What could f be? I don't know. I didn't. As long as it has an inverse. So what do these two do? Cancel. So I get x minus 7 equals, now here's the beautiful part, what's f inverse of 3?
Negative
2.
So if that was given.
That has to be given, or else you can't do that step.
Yeah.
Isn't it negative 2?
Yeah. Negative 2. Sorry. And now that you just solve.
Yeah, you make it look so easy.
How is 3 negative 7?
This is given.
So we don't worry about it, we just assume.
Let me do something just like this. Hold on. If I add 5 plus. All right, just go with me here for a second. It's the same basic thing, except what change have I made? Here, I'm very general about the f. I don't know what the hell. All I know is that an inverse exists, and they told me something about it. What do you do? Yes, sir.
Oh, I see.
So I'm just very specific about what f I'm using. I'm using the cube function, right? And does a cube function have an inverse?
Yeah, keep it.
Cube root. Yeah, cube function, what does it look like? Does it pass the horizontal line test? Cube looks like this, right?
Yeah.
Basically, make that bigger. It passes the horizontal line test, so it's got an inverse. Okay, cool. So when I subtract 5, I apply the inverse operation, which is cube root. Now here, I applied the inverse operation, which was f inverse. Because I don't know what the hell f is. I can't, is it a root? I don't know. But here I can tell. The cube root is the opposite. So I get x minus 7. Was this ugly thing, I add 7. But I want to show you what's actually happening here is, this is the more general way to say what we did there. Here I just know exactly what the function is, so I know exactly what the inverse function is. Here, I got a function. Its inverse exists, so I'm going to do that so that it dies. So I can get my x by itself, right? Okay, this is the same thing you've been doing since math, the end of Math 88. You learn how to solve equations. Yeah?
How do you know F inverse is,
It's got to be given to me. Here, did I need it given to me? If I would have picked better numbers, let's say this was 27. Do I need somebody to give this to me, that cube root of 27 is 3? No, because I can see, I know it's 3. Here they had to tell me this because I don't even know what the function is. They had to tell me what that is ahead of time so I can finish this out. Okay, sort of. So now I've warned you that I like that problem. That kind of problem. Okay. All right, so let me give you guys several to try on your own. As soon as I remember out of time, I shoot. Oh.
These are the same functions, right? I don't see how come that means this value has to equal this value. So you just have to find the number for x. I mean, that works too, I guess. But I just have to
All right, so there's number 1. Graph inverse, f inverse. I'm pretty much telling you that an inverse exists, and of course it does, because again it passes the horizontal line test.
And 2 and 4 and 2, or
Yeah.
negative 4 and, negative 4 and 2. Is that a 2 or a 3? It's kind of like a 2.5. Is it negative 4?
This here, this is negative 4, 3, 0, 0. This is 1, negative 3. You'll be happy to know that if I do get this kind of problem on a test, I'll actually use computer software to generate the graph. I'll be doing my own and then copying that. Yeah.
So it's,
Oh, yeah, right there. The idea here is you have to do plus or minus. And it just really is applied to one side. So it's, you know, if you plug in a negative 2 here, it could be a 2 there. So do both x1 and x2 have to be the same if the outputs are the same?
You would get the same output if you put a 2 versus a negative.
So that's not, I mean, it's not a
And then the same kind of thing happens.
What was the question? Did you say try to solve? Yeah, remember? I should have
Find the inverse.
24.
18.
Oh, okay. So it says,
It tells you 5, G inverse of 5. Which really means when is this equal to 5, given that x has to be greater than 2. Equal to 5. Subtract 5, factor it.
and then you're going to throw out the x1 that's less than negative 2. Because they restricted their domain. Yeah.
Or 2x minus 7 cube or power 5?
Fifth power. Yeah. It's a fifth power there. I like that one, Steve.
Can I ask you a question about test questions
Mm-hmm.
right now? Okay. Would this be?
This way.
Okay, sorry.
Sure.
After you made the changes, because I think
As long as you do the up one last, so I was throwing some people off. So reflected.
Y equals that, and then switch X and Y.
Yeah, because this takes the outputs, whatever they were, and makes them the opposite. So it's up here, so it should go across the x-axis.
oh, it should?
Yep.
Okay, well, that's what I did.
Oh, you put y there.
I know, I
But you
put
did
Y,
x.
but I
Okay,
did
you
X.
wrote the wrong. So you did the right.
Okay, that's what I was confused about.
But you have to do that.
First.
Order operations actually works here as long as you do that last.
That one
You're
was?
fine.
I did
Yeah.
Cool, because the
Good.
7 goes in
Then
that
you should be
there,
fine.
the 2 goes
And,
in there, and all goes over 2. That's
Let
awesome.
me see.
That is pretty cool.
So you took it back to
That's pretty cool how that works.
reflect. Back to reflect should be at 2. Yeah, it doesn't look like you did the up one last.
Did I reflect it
Oh,
when I
sorry.
left it left?
I did it last.
Oh, so this is at 2, so if you reflect it should be negative 2.
I know, and then
But it's cool how it
left.
works.
and then up.
And then up.
Yep.
Okay, well that's fine. That was
Yeah.
just, thanks.
You want-
That's cool how that works.
All right, let's take a look here. What points would F inverse go through? 3, negative
3,
4,
negative 4, 0, 0,
0, 0,
negative 3, 1,
negative 3, 1,
and
negative 4, 3.
3.
All right, so it goes through there.
Yeah.
It goes through there.
Yeah.
So far, it's not very interesting. Now the trick to this, you got to realize, well, we'll see. Then it goes through also negative 3, 1. And it goes through negative 4, 3, 3, negative 4, 4. Okay. So do you see how, remember, I'm going to flip it around y equals x. So it's like that piece comes up here. So that kind of helps you. So now I can put that shape in there. If I turn right. And now it's going to come back down to here. So that's kind of nifty. Does that make sense? So this just reflects there. There it is. And this just reflects there. All right, cool. That leads to a very interesting thing about this one. Let's do this one first. So I bring the y back in. I change the y and the x. And then I see if we do all this at once.
X plus 2,
Add 2, take the
5th root.
fifth root. All right, let's stop there. And I add 7 and
Divide by 2.
divide by 2. So I end up with y equals fifth root of x plus 2 plus 7
Divided by 2.
all over 2. And that's F inverse.
Yeah.
How's that?
Yeah. Yeah.
Now this one's a little bit funky. It's not necessarily difficult to do. You switch the x and the y. How do I solve for y? You know. Now this looks simple, but it might give us some trouble. Where's the y though? I'm trying to solve for y. It's currently on the bottom. That's the worst place for a variable to be I'm trying to solve for. So the first thing I do is multiply it the hell up. Now some of you guys might know the ultimate shortcut you should learn from algebra is if you have something like this, they can just switch places.
Yep.
It's the same little silly thing like 5 equals 10 divided by 2.
Y equals 2.
Therefore 2 equals 10 divided by 5. That's ground shaking. But that helps us with equations. Those just switch places. If 2 divided by y is x, then 2 divided by x must be y. Which tells me what about this function?
Inverse is the same as
It is its own inverse.
Oh.
If you think about where the mirror is, what should happen graphically with a function in order for it to be its own inverse? When you flip it, it's got to go right back. It has to already be symmetric with respect to y equals x. Sorry. Right, so the most simple equation, the most simple thing that is its own inverse is y equals x, because it's on the y equals x line. Ooh. The more interesting ones are the ones that look like this, which is actually what that looks like. So when you flip this, whoo, it goes right back on top of itself. So it's its own inverse.
Isn't there another special case for those? Are those parabola or hyperbola?
That's the type of a hyperbola. Yeah.
Right. Isn't that like a special case of it? Or, I don't know.
But this is the thing that makes it special is that it's a rotated hyperbola. Most hyperbolas live on one of the axes, and then they wouldn't be their own inverse because they're not in the right place for y equals x. These are in the right place for y equals x.
All right, they're not on them.
Cool. So if I have a rotated hyperbola, it could be its own inverse. Okay. Is that kind of cool? Is that all right? All right. So the last thing here, let me just show them these. Nah, I think I'll leave that for you guys. Oh yeah. There are a couple that have you graphing things in a graphing calculator, and they ask you, does it look like it's invertible? So, of course, you're just looking to see if it comes back on itself, right? So it's just, graph it correctly, get the window in the right place. You should be able to see if it's coming back on itself, has a little dip. It's not going to pass the horizontal line test, so it won't have an inverse. Here's the one thing I wanted to show you. Does this have an inverse or no? Tears. What does it not pass?
Horizontal line test.
So it does not have an inverse. Now what we're considering is, Jeff, man, the opposite of a square is a square root. But does it come out with a single answer? No. If I have x squared equals 9, when I apply a square root, I get 2 answers. That's exactly the opposite of a one-to-one. It's no good. But I can do one thing that will make this an invertible function. Sounded drunk. Make this a one-to-one function. That's easier to say. What's the problem with this function? How can I remove the problem? Where exactly does the problem start? Yeah, right here. If I could go either way from there, I'd be fine. If I could just erase that piece, for example, that would be awesome, right? And of course, you do that by just saying, all right, f of x is x squared equal to 0. Problem solved. Right? So you'll see that in some of the problems. They'll have squares in there, and they're asking about inverses, and you'll be like, what the hell, man? Jeff said this. Look to see they probably restricted the domain in the right way. Right? It took off that other half. So if I did flip this over the line, what does it become? Exactly the thing we'd hope it becomes. It becomes the square root. Kick ass. Okay.
Would it then be the range after you got an inverse?
Say again?
Would it then be the range after you got
I like that you're saying that, because that's the other thing I forgot. I knew there was something I forgot. If I had a function whose domain was 0 to 7 and whose range was -4 to 5, okay, so far so good? The inverse function, what would its domain and range be? Now, when you say opposite, what do you mean? Please don't say 7 to 0, because intervals have to go from small to big. You can't mess with that. But you're forgetting the real. This is not a point. Where are my x's? Where are my x's? Where are my x's? Domain. Thank you. Where are my y's? Range. So what happens for an inverse function? The x's and the y's change. So this guy's domain is this guy's range.
Yeah.
So if I would have made a slightly more interesting function there, I could have made that point. But unfortunately, their range and domain are the same. So kind of lose that point. It's too bad for me. But in general, I mean, that just is beautiful. It goes along with the whole idea of switching x and y. Every single formulation that I've used about inverse functions have somehow fundamentally been about switching the x and the y. So is this. Domain and range switches. Why? Because the x's and y's do. Leave me alone. Right? Maybe. All right. And I'm dragging. I'm sorry. Hopefully I'm making some sense here. Well, I'm not feeling well. I think now's my time for the flu, maybe. I don't know. Oh, yay, Jeff. Should have got that flu shot. Okay. A little preview, and then we'll head out. I am going to go slightly fast through the first two sections of Chapter 3, so you might want to look ahead. It's a review of quadratic formula and quadratic functions, not quadratic formula, polynomial graphs and things like that. So I keep telling you about x cubed. You have to know what that looks like. You with me? The really meaty part of Chapter 3 is where we're going to learn something really kick-ass cool, which if you don't know it, you're going to hate the sound of it. It's called synthetic division. And it is, there, see that reaction? So if you don't know it, I did not pay them ahead of time to go, yeah. It's awesome. Yeah.
I was just wondering when you were going to put, if there was homework up on WebAssign.
I finally just put 2.7 up.
Oh, did you? Okay.
Yeah, so now I'll put some more up there. Yeah, thank you. So all of Chapter 3 is really devoted to analyzing the hell out of polynomials and their graphs. And I think I told you the first day. Who remembers what I basically call 176? Graphing hell. Right, didn't I say that? If I didn't, there it is. It gets you ready for calculus by just analyzing the hell out of graphs of functions and non-functions and whatever. So this is our first little real foray into that, is analyzing the hell out of polynomial graphs. Sounds exciting, I know, but
Do we look excited?
yes, you all have that. Okay, Joe. All right, that's plenty. Hopefully I'll see you next week.
You should have asked the rest.